of our faculty program in sensor data analytics organized by Indian Institute of Information Technology, Kottayam. We came to know that yesterday's sessions were fruitful for all the participants from your feedbacks we collected yesterday. So we are also hoping for another fruitful day with the resource persons we have today. So for the first session, we have Dr. Jayakrishna Sahu, Assistant Professor, IIIT Kottayam, as our resource person. Let's have a brief introduction about the resource person. Dr. Jayakrishna Sahu completed his MSc Mathematics from Utkal University in 2005 and obtained his MTech in Computer Science and Engineering from IIIT Bhubaneswar. Received his PhD with specialization in data mining from IIT Kharagpur. He has been associated with IIIT Kottayam since July 2019. Prior to this, he has experience of working with BML Munyal University, Gurgaon, in the capacity of assistant professor at the Department of Computer Science and Engineering. Dr. Sahu has also worked as an ad hoc faculty in the Department of Computer Applications, NIT Jamshedpur. His current research interests include data mining, machine learning, and cryptography. So with immense pleasure, I would like to hand over the session to Dr. Sahu. Over to you, sir.
Yeah. Thank you, Selvin, for your nice introduction. So without any time delay, let me proceed with the session. So on today's session, the topic of the session is sensor data analytics. So these are some outflow of the context. We will go for introduction followed by sensor data analytics. Then as all the statistical techniques, whatever we are using in the traditional data analytics, also almost all the techniques are used in sensor data analytics. So that's why we'll go for that machine learning for sensor data. Then we'll come for supervised ML and unsupervised ML, and neural networks and deep learning. Then we'll go for predictive modeling. So in the first, whenever you go for an introduction to sensor analytics, sensor data analytics. So here, due to the technology advancement, we are getting very cheap and sensors are easily available for each type of task. So GPS enabled devices also, pedometers, accelerometers. So those kind of sensors are used to collect different kinds of data. So it leads to the tremendous amounts of real-time data. So that it should be needed in the mining should be needed. Analytic, what is the insights should be discovered. So since that these sensors are more, so and every per second they are generating much more data. So this is that the data size becomes overwhelming. Okay, so you are getting many more data. So you may attend from simple data analytics to big data analytics also. However, to be useful, the data needs to be handled in a way that is organized and in controlled manner. So that's why the sensor data need to be mined. And of course, once we are collecting the data, it depends upon the context. So the context means if you are using, suppose, say, mobile devices and you are collecting the GPS data, so you may analyze for location oriented analysis. Okay, so and their corresponding application. Similarly, if you are collecting data from RFID tags, so this also you can because the RFID contains most of noise, so that noise analysis, outliers, or those kind of things also this data can be useful. Similarly, if you go for any sensors used in military applications, so there you have to use for unusual events or activity. That's why that activity might be include visual and might be data generated from visual and audio cameras, or some sensitimeters for tracking movements of large objects. Okay. Suppose so sensors are also deployed in the context of a wide variety of environmental applications. So such as detecting the weather, so climate trends, tracking pollution levels in water networks. So depending upon the application domain and the context, different type of sensors will generate different type of data. So that's why there is the need of analyzing those data. So in the world of this Internet of Things, it creates massive amounts of data from sensors is common. And one of the biggest challenges is that not only that it is restricted to a particular application, say transport, okay. Also, it is a challenging task for data management standpoint also. Suppose that our modern jet engines are fitted with thousands of sensors that generate open 10 GB of data per second. So analyzing this amount of data in the most efficient manner. So obviously it comes under data analytics, and what are the techniques we are using for traditional data analytics, those techniques can be extended. So what are the services we'll get after analytics? Might be personal service, just like a lifestyle assistant, a mood-based service, neutral entertainment. Similarly, on community-based community services like healthcare sector, OLS hospital, remote patient monitoring, emergency coordination. In industrial services like asset monitoring, store of the future, food processing tracking, and many more also. Few of them are listed here. So these are services. So what is the why we're going for sensor data and what is its need and what type of data analysis we can perform here? So the importance of sensor data from smart objects is realized only when analysis of the data leads to actionable business intelligence and insights. So only when we can able to realize the what is its importance, once we'll analyze it, and those results after the analysis, what are the outcomes, those will give some insight that will, if it is application on business, it will improve your business. If it is application to security, then your security should be improved. So it typically broken down by the types of results that are produced. Okay. So based on that, what are the types of data analysis? You will see it is either descriptive or diagnostic, predictive, prospective. So in the descriptive, the question says you are analyzing something. So what is happening? But in diagnostic, you will do why did it happen? You are finding the reason for that one. But in the predictive questions like this, now you will predict or forecasting what is likely to happen in the near future. In the perspective, you have to take the decision. Okay, so what should I do about it if something will happen? So based on the based upon the analysis or types of results you are produced, based upon that, the analysis can be categorized into four types: descriptive, diagnostic, predictive, and perspective. The technology to do this, we can use big data technology that collect, integrate, process, aggregate, visualize. Or you may use the only one line is written here, big data, but all the data analytic techniques you can use here, data mining or data analytics techniques. Also machine learning or AI techniques can be used. So how to get the data? Data are from sensors, okay? So event alarms, geolocations, video, social media. So many types of data. So machines and sensors also there. So data can be generated and the corresponding technology will use, and based upon the technology, the result, it may go for descriptive, diagnostic, or predictive, or perspective. So in the descriptive data analytics, tells what is happening either now or in the past. For example, a thermometer, for a thermometer sensor, suppose there is a sensor thermometer in a truck engine, reports temperature values at every second. So at every second, we are collecting the temperature values. So from the descriptive analysis perspective, you can pull this data at any moment to gain insight into the current operating condition of the truck engine. If the temperature values is too high, so your what is happening, your analysis, if the temperature values are too high, then there may be a cooling problem, or the engine may be experiencing too much load. So your analysis get what is happening. You are only finding out what is going on by analyzing the data. In case of a diagnostic, when you are interested in finding the reason why it is happening. So that time you are going for diagnostic. So just like previous example, now in the previous type, you are finding the temperature is high, something happening, or low, something happening. So the question is why the truck engine failed. So based on that temperature analysis, you may give a reason why the truck engine failed. So just like that the temperature of the engine was too high and the engine overheated. That's why the engine failed. So if you apply diagnostic analysis across the data generated by a wide range of smart objects, can provide you a clear picture of why a problem or an event occurs. So you are diagnostic the reason behind your problem. In case of predictive, so you have to forecast before they occur. So I mean in future, what will happen in the future. So continues with the previous example, if you have a historical values of temperatures for the truck engine, that predictive analysis could provide an estimation on the remaining life of certain components in the engine. These components could then be proactively replaced before failure occurs. If you predict it, suppose some parts of the engine may fail after this much uses or after certain time, then before that event happens, before its failure, you may replace. Or If temperature values of the truck engine start to rise slowly over time, this could indicate the need for an oil change or some other sort of engine cooling maintenance. So this predictive means you may think about forecasting. So you are predicting what will happen in the near future by analyzing the past data. In case of perspective analysis, so it is a little bit one step ahead of the predictive, and it recommends solutions for upcoming problems. So if something will happen, it will give you a solution. It will give you a rule. So a perspective analysis of the temperature data from the truck engine might calculate various alternatives to cost effectively maintain our truck. So it gives a solution. These calculations could range from the cost necessary for more frequent oil changes and cooling maintenance to installing new cooling equipment and the engine, or upgrading to a lease on a model with more powerful engine. So when you are doing perspective data analysis, it looks at a variety of factors and makes the appropriate recommendation. So if you say recommended system, that simplest example, it is one type of perspective in with the predictor, obviously. So when you go for recommend, first you predict, then you have to do the recommendation, provide the solution. So if you see, both predictive and perspective are more resource intensive and increases the complexity, because diagnosed, we have the data, from that you have to analyze. Similarly for descriptive. But for the predictive and perspective, you are predicting the future and you are providing the solution. So it is more complex than the descriptive and diagnosis. For descriptive analysis, we are most of the people, many times we are using the statistical things. For diagnostic also. But for predictive and perspective, we are applying that machine learning techniques. Okay. So we will not give that descriptive and diagnostic, because it is all the data analysis techniques. What is that your hypothesis testing and that chi-square correlation analysis, mean, median, mode, everything, every statistical analysis you can perform here. That aggregation, some summarization, everything. But for predictive and perspective analysis, we have to take the help of machine learning. So if you see that the machine learning things for the sensor data, so you see here, if it is a machine learning, then it either supervised or unsupervised or reinforcement. Then supervised might be classification or regression, unsupervised might be clustering. This is some general hierarchy of machine learning techniques. So here, obviously, dimension reduction is also there. So many other pre-processing techniques and selection techniques are there. So out of that, and also model accuracy and those kind of things, model evaluation, measurement, those kind of things also. So what supervised learning takes the advantage? The situation where we have knows the label data sets, so the class label is known, or some guidance principle is there. Some teacher is guiding you with your result. Okay. So that time you, that is the advantage of supervised learning. It can be further divided to classification, regression, depending upon the task. In case of unsupervised learning, so it does not rely on the labeled data for training. It does not rely on the labeled data for training, and without means without class label. Okay, if it wants to find the interesting pattern or unseen patterns there. And in case of reinforcement learning, it relies on an external feedback mechanism. So maybe our mechanisms. So based on the result, and the system will try to optimize itself. So this is the general workflow of machine learning, both supervised and unsupervised machine learning techniques. So if you see here, we have the sensor data. Then it is followed by pre-processing techniques. So here you may handle that noise removals and missing values, filling of missing values or removal. So making the data set smooth. Okay. Then once you do some pre-processing techniques, so data in clean and you remove noise also. Okay. So now it is ready for feature extraction. So they are let's say process the data is further reduced into features. So once data is pre-processed, then you have to reduce it to features. That features is nothing but it describes the incoming data. So what is the data you are getting? So somehow not because you are in pre-process, you are removing something. So it describes the incoming data data stream in some way. Okay. So not the complete, but it describes the data. So might be some features might be what is the average mean of the signal, or maybe a deviation, standard deviation. Okay. Maybe what are the spectral components, or what is the minimum value, maximum value. These are some examples of features when you are considering a signal data, sensor signal data. Then that data stream, once you got the feature extraction, then the data stream is partitioned into training and validation, or you can say testing data, or training, testing, validation. You have to split it. Then you have to choose the appropriate model. So training. So there you may use a help of statistics for hypothesis test of the result. Then you will test the model in the testing data, and you are getting some model scores. So once you generate your model, you are getting some that accuracy up to some level. Then you have to deploy that model to execute unknown data, and then depending upon your classification or regression or class, whatever may be your model, based upon that, the unknown data will be modeled. Okay, either if it is a classification problem, then it will classify. If it is a prediction problem, the unknown data will be predicted. What is its value? Means it depends what is the target value based on that. And if it is same classification or prediction, okay, supervised and unsupervised. Hence, once we go for sensor data, so then we'll go for sensor data acquisition. So how we'll collect sensor data. So there are depending, it depends on what are the sensor types. Based on that also, you can get different type of data. Not all data are the same. Obviously, then features of sensor, and it is structured data or unstructured data. Then the data quality depends on data quality and inherent variability also. In structured and unstructured data, based upon the if the data you can it is either a structure, or suppose a temperature sensor data, it is a structure, but if you are considering image or some motion data, then it is unstructured. Then we'll go for data quality. So data quality means that can be computed during the transmission of the signal. Okay. During the transmission of the signal, you can that should be computed. It means how much that you are losing the data, you are losing, or how much knowledge there. The quality of the data should be maintained, so that that data should be no missing values. The transmitter protocol should be there, error checking mechanisms, so and data recovery features also. So if the data is also collected, if there is outliers also present, that should be removed. So for outliers remover, you may consider that statistical distribution. Okay. Also, that data quality issues that what is your sensor sampling rate, and what is the data resolution. Those factors also affect your data quality. And if the sensors are connected to a network, so there might be a what is the communication capability, that that factor also taken into consideration. And inherent variability here for suppose for many applications, you are suppose machines are there that monitor the activities, or say, so the data might be stationary or non-stationary. Means time series data you may consider. So if it is non-stationary, that it depends upon the statistical properties of the data with time varying properties. So the variations may depend on when the data is collected and observed. If that is the thing, you may consider some bias factor, or you may consider the concept of drifting. Those kind of things we are considering here. Then we'll go for one by one. In case of sensor types, depending upon the sensor types, the different type of data will be generated. If it is thermal sensors, so we can get the temperature or heat sensors. If it is electromagnetic sensor, then electrical resistance, voltage, power sensors are there. Magnetism sensors, metal detectors, radar. In mechanical, acceleration, position, pressure, switch, liquid sensors. In chemical, you can find that smell or oxygen sensors. Optical radiations, light sensors, infrared sensors, proximity sensors. Similarly, in acoustic sound sensors, also motion sensors are there. A speedometer, okay, tachometer, odometer. Orientation sensors, gyroscope. Similar light sensors are there, detecting light intensity, density, reflection, color, temperature, type of light. Rich information and very low cost. light sensors because they are very cost is very low. Similarly, for visual information, you may got for camera sensors. So visual information about the environment, processing power and storage needs are often large. Users feel uncomfortable. So if the camera sensor is there. Location sensor, either global positioning system GPS is mostly used. So it codes location information. So cellular network infrastructure, it depends upon that one. Global, that GSM. So these are the, so when you go for light sensors, so what are the features you will get? Either you will get that what I told you, light intensity, density, reflection, color, temperature, light. So in the location, you are getting the location, location of the user. So if you are using audio or a microphone sensor, so what are the features you will extract? What are the features? So interesting information are noise level, type of input, base frequency. What is the minimal processing speed? Multiple microphones, there are not. Richer information. It is very cheap. Can it be extended for speech recognition by using more processing power? Also, ultrasonic sensors are there to augment human sensory capabilities. So if you are using accelerometers, so what are the features? The features are on the inclination, motion, acceleration of the device, how much inclined, what is the motion. Typically users hit mercury switches, angular sensors. So in interesting examination of usage patterns, some behavior analysis or something you may use. In TOS sensor, we can can reduce the energy consumption operative in the user's hand. If air sensor you are using, then some hints what is closing door and some features should be like that. If you are using body in temperature sensor in your body, then it will observe what is the temperature of your body and those kind of things. So depending upon the sensor, different features will be extracted. The point is that one only. So based on the features, we have to, you consider which features are mostly variable, mostly important, and correlation should be find out. Those type of statistical tests we may perform. So in magnetic field, tail sensors, no power sensors, biosensors. Okay. So in biosensors, you can skin resistance, blood pressure, okay, applicable in sports and medical applications. Emotional state of user may be obtained. So the point is only depending upon your type of sensors and depending upon your applications, you have to extract the features. So once you have identified the features, out of those features, you have to perform some feature extraction. So in the context of sensor data, so you have suppose 50-60 features are there, not all the features are important. So you may do some feature extraction and say feature selection, which features are important and which features are not important. So you may use many machine learning algorithms for feature extraction from the data, sensor data input. Out of that also you may use various signal processing techniques for this for extracting the features. So when you are using some signal processing techniques to extract the features, so based upon the techniques, it can be categorized into either in time domain or frequency domain or time frequency domain features. So you know, time domain features include traditional descriptive statistics. So you may calculate the mean, you may calculate the variance, you may check the skewness of the data, you may check the kurtosis, zero crossing rate, okay, rest factor, and so on. So mean that if X So here x is a real number, xt is a real number, and it represents a measurement of data at time t. And if there are n segment, means in the, since you are considering sensor data, if you are considering a particular window or particular segment, and there are n number of data points that at time, data time, then the mean is by this formula, it is well known, variance also well known, skewness, kurtosis, zero crossing rate. So these things are you may do for in case of time domain features. But in case of frequency domain features, you may go for fast Fourier transform. So frequency specific informations are often invisible in the time domain. If you apply the FFT, you can convert a signal into frequency domain. And so the corresponding algorithm you have to use, it is known as a discrete Fourier transformation. So you can get many works on this. So how the sensor signal section data is converted to features using FFT and DFT. So here the frequency components in the DFT reveal periodicity of time series raw sensor data. So nowadays many more sophisticated tools also exist. For example, you may consider a bispectrum or trispectrum, or some higher statistics spectrum techniques also there. In time frequency feature, so here whatever the previously we calculate the mean, median, those kind of things, so those are suitable for stationary data. But for non-stationary data, means where statistical properties are not means they may vary, that not hold. So there one technique used that short time Fourier transform, which is computed by Fourier transform of segmented data after dividing the entire time series into multiple segments. So the entire time series data is divided into multiple segments, and for each segment you will apply the FFT within DFT. Another technique used for this type of case is wavelets. So it is used generally for comprehension and denoising. It can also be used for time frequency features for machine learning purposes. Okay. So if here if you are applying the wavelet, here, then suppose the signal is S1, then that S1 using some techniques, okay, that wavelet function you have to use here. It can be one is it can be partitioned into two, that high pass and a low pass. Then it is assigned to D1 and A1, and it will go like that. So every time you will partition the signal into using some filter function you have to use. Using that function, you have to partition that into high and low pass signals. Okay. So in this figure, you see 4 level discrete wavelet transformation. So using discrimination filters. Then once you extract the features, then you may go for dimension reduction. And for dimension reduction, you mostly prefer mechanism is principal component analysis, where you are projecting the data along the principal axis. So in principal component analysis, means you are projecting the data in the principal analysis to reduce the, and then you are considering the data which are lie or close to the principal axis and ignoring the other dimension. And independent component analysis is also an extension of PCA. So here it extracts the statistically independent components. Kernel PCA, also an extension of principal component analysis. So here the kernel function is used if the data is not separable in the current space. Then in the higher dimension space, using the kernel function, you are transferring the data to a higher dimension. And there you are applying the principal component analysis. And you may use a linear discriminant analysis. And this is used for classification. You may use it for hello. You may that linear discriminant analysis. You may use it for classification, but you may use it for also dimension reduction. And here, in case of LDA, so the difference from how it differs from PCA is that PCA only considers the dimension reduction on only one dimension, that it projects on one dimension, the principal axis. But in LDA, it considers both the variations. Okay, inside that intra-cluster and that extra-cluster variations. It considers both. Also, for particular to sensor data, most of the Haar wavelet transform is used. So suppose you are collecting 10,000 data per second from a temperature sensor, suppose say. So that we see almost all data are similar. So instead of considering all 10,000 data, you may be interested to consider only 1 or 2 or 3 or 4. So which data you have to select? So then that time you are partitioning that entire window to 2 parts. Again, 2 parts take the mean. So there that Haar will work in this manner. Okay. So these are some dimension reduction techniques used in sensor data. Sensor data reduction, you can say. Then on features, one should so you feature selection. Either you go for unsupervised feature selection or supervised feature selection. So based on the in unsupervised feature selection, the features will be selected based on the performance of the unsupervised learning. For example, clustering algorithm, the guide the selection. So how good your cluster is. So based on that, you may select the feature. And in case of supervised feature selection also, depends the performance of the prediction or regression or classification. Also, in some particular problems, that the feature selection can be done manually also by selecting. If you know the domain, if you are a domain expert, you can select the features manually also, because you know this feature is more important to the output decision. Or you may use different algorithms, genetic algorithms, bio-inspired algorithms, but evolution algorithms, differential evolution, simulated annealing. Okay, those kind of bio-inspired algorithm or evolution algorithm can be used to select the features also. So this kind of so feature selection techniques is used, and it is also important. Why in the sensor data you have to select the features or variable selection is important. So it should be selected carefully, because it has a direct impact on the model accuracy. But at the same time, adding too many features can lead the model for overfitting. So means it describes a random error. So in the training data, you may have 100% accuracy, or your accuracy is up to full complete. Okay, so your model fully fits. Okay, so no error, your accuracy is 100% like that. But they have poor predictive performance. So when you are applying that model on the test data, the performance might be poor. Okay, you are not getting the result of what you are expecting or what it should be. For example, if you see this graph, there are suppose 20 data points. Okay, so that blue dots represent the 20 data points. Suppose we use some interpolation to feed this data, and or any regression or interpolation, whatever maybe, and we got that this data is fitted with this 15-degree polynomial. So once we see the 15-degree polynomial, you see almost all data with a little error. Okay, if you assume some error, that threshold value within some range, then almost all data satisfy this equation. Okay, so this polynomial function that feed the core, it's very nice for the considering this training data points. But whenever a new data set collected from the same population, from the same domain, okay, a new data set is collected, may not fit for this particular core. Okay, it may not be fit to this core, or it will not lie in the path of this core. Okay, so feature selection, variable selection plays an important role. So in sensor data pre-processing techniques, if we see the input data is what are the type of input data, if it is video, sensors use CCD, COMS, that compression techniques, that MPEG H.26x, I will answer this once towards the end of the session. I'll answer these questions towards the end of the session. So data processing techniques, if you are input data, video, that sensors your CCD and CMS, then the processing techniques use as compression and facial detection techniques, data streaming techniques, those kind of techniques you can use. If audio data and sensors you are using microphone, then compression MPEGX, G.7xx, AAC, audio data processing techniques, voice recognition. If you input data is position, GPS or radio frequency system, position detection, map data, mapping, addressing, and time detection. If it is bio or medical or healthcare data set, the sensors are either EEG, ECG, or EMG, PPG, JS, skin temperature, respiration, blood pressure, those kind of things. So what is the heart rate extraction, stress level, emotion estimation, alpha wave detection, health monitoring. Okay. So in the environment, if the data is input data is your environment, then light, humidity, temperature, ultraviolet sensor, noise detection, awareness environment, purpose is awareness environment. If movement, input data is your movement, then falling detection, gesture recognition, human interference. So the techniques you may use data mining techniques to this kind of problems, like facial detection technique, voice recognition, and stress level detection, health monitoring, gesture recognition, falling detection, those kind of things we can use data mining and data structuring techniques. Also feature extraction techniques will be used. Again, come to the next part. Once the feature is extracted. Hello. Hello.
It's fine.
Then coming to once the feature is extracted, then it will you have to fit for a model. And as we discussed previously, this might be your depending upon the data or the if it is labeled data or unlabeled data. Based upon that, the learning method should be applied. So you may apply if the data is labeled, you may go for supervised learning. If the data is not labeled, you may go for unsupervised learning. So in the supervised learning, that you are generating some linear models. For example, logistic regression, support vector machine. And some nonlinear methods are just like k nearest neighbors, naive Bayes, decision tree classification, random forest classification. So particularly in case of supervised, the types of learning is either regression or classification. So that regression, whatever you may lasso regression or multivariate regression, those kind of regressions you can easily apply here in case of predictive modeling. Then if you are applying some nonlinear models, then KNN algorithm, naive Bayes, decision tree, random forest. But once you apply the model, then we have to evaluate the model. That will either loss function you have to use, log loss function, confusion matrix, or you may use ROC curves. So logistic regression, this is log of, so this is the either 0, 1, it is in between these two. This 0.5 is the threshold value. So it depends upon the type of data, it might be binomial or multinomial or ordinal. But the point is you can use this, then how to use this logistic regression in case of sensor data. So as we know that what I told you, few said what is xi, it is the time that the data at a particular timestamp 1. Similarly, x2 is the next timestamp, so they are collected on different times, but for same data. So these things can be used by a logistic regression. Similarly, you can apply regression, but that depends upon your class type, that label. If you are using for a prediction and your class type is not binomial or ordinal or multinomial, it is just continuous values, then you can go for regression. But if it is binomial, multinomial, or ordinal, you may go for logistic regression. Similarly, it is nothing but a numerical interpolation over the data, over the past data. And so that the output will give you the future data. So once you build what is this y in terms of x1, x2, x3, then you put the previous data on data to x coordinates, and then you will get what is the predictor value y. Then apply the probability that either that's a log function there. So if it is this value will be between 0 above this threshold, it will go 1, below it will go 0. This is for binomial. In KNN, so computes the distance between the new data point with every training example. So suppose this is one category, this is another category of data. So this is the new data point. So distance between this data to with respect to each data point of the both the categories will be computed. So for distance can be computed based on either Euclidean distance or Hamming distance or Manhattan distance or LP norm, depending upon the. Then once you compute the distance from this point to every data point of the category, then you have to pick the k entries in the data set which are closest to the new data point. So closest in the sense that the distance is minimum. Then it does the majority vote. So suppose there are 10 data points near to this point. So out of 10 data points, how many data points are in category B and how many data points in category A? So then it does the majority vote, and the most of common class level among those k entries will be the class of the new data point. And so it only based on the distance and k nearest neighborhoods based on the closest point. In support vector machine, for suppose a 2 classifier, we'll think about multiple classifier methods. A multiple class, we'll go for 2 class problem now. Suppose there are 2 class. So the goal of support SVM is to create a baseline or decision boundary that can segregate n-dimensional space into classes. So here, the data that you have, your aim is to find a hyperplane that will partition the data set into 2 parts so that the future data can be categorized into 1 part. And so this best decision boundary is called hyperplane. So SVM chooses the extreme points or vectors that help in creating the hyperplane. So suppose this is blue colors are 1 and this is green colors and another class. So if you find a separation between the 2 classes, this is the region where we can able to separate. And these points are known as support vectors, so they are nearer to the boundary. And the line which parallel to these support vectors and lies at both sides at an optimum distance, it is known as the maximal margin of the hyperplane. So in this way, suppose once you got this hyperplane, then one new data point will come, you will put in this hyperplane model. This is the equation, this is the linear model based on the parameter. Okay, so sorry, based on the weightage. Weight means if y is equal to w1x1 plus w2x2 plus w3x3. So based on the weight, it's a linear model, not on the part x value. So you put the x value on that equation. If it is lie on this, then it is on the hyperplane. You cannot classify it properly. But if it is greater than, then it is in this side, so it is classified as blue. And if it is below this, it is classified as green. So in this way, you have to model training means from the data, you have to classify, you have to find the equation of the line, this equation of the hyperplane. And in the prediction, in the new data point, will put on that equation, and then it will check for in which side of that the data lies on which side of the hyperplane. Based on that, the output will be generated. Just like here, there is past label data. Based upon that, model training means you are getting this here, you are getting this linear equation of hyperplane, and a new data will be there for prediction, and it will be identified at which side it will lie. Based upon that, it will identify its cat. So there are many possible lines exist, but you have to choose the optimal hyperplane. So if you look at these figures, so many lines exist. Okay, here these 2 classes can be classified into many lines. For example, here 2 lines has been given, but you can do any line parallel to these 2 lines. Okay, this line are parallel lines and this line parallel lines to satisfy. But out of those, you have to choose the optimal hyperplane. So in the third figure, it has been shown that this is the optimal hyperplane that lies equidistant from the support vectors of the both class. So some support vectors are the boundary points. Okay, those are nearer to the margin. And this is known as the maximal margin. And this one support vector, so here you will get 1, 2, and 3 support vectors. So the equation of the hyperplane does not depend upon the entire data points. It only depends upon the support vectors. Because in the derivation, if you go for support vector machine derivation, the equation of hyperplane easily can be derived from the support vectors. Then Naive Bayes classifier, it is based on the Bayes theorem. So that a conditional probability. So that used to determine the probability of a hypothesis with prior knowledge. So that is prior. So both prior and prior probability will be used to build the model. Then you will use the posterior probability to predict the model. So this P A by B is the posterior probability. Probability of hypothesis A on the observed event, and you have to calculate what is the probability in each class, then take the maximum. So Navier-Weiss algorithm. Similarly, because it is well-known algorithm, and similarly that machine learned that decision tree. In decision tree algorithm, you have to begin with the tree with root node, say suppose yes, which contains complete data set. So here the entire data set, from the data set you have to split the data set one recursive manner. It's such that the entire data set is lies on the root, and once we down the root, the data set is partitioned based on some principle or some attribute, we can say. Okay. So begin with the tree with the root node. So find the best attribute in the data set using attribute selection mechanism. There are various attribute selection measures are there. Based on that, we will select the which attribute will be the best attribute for the splitting. So might be information gain or Gini index or gain ratio. So there are various measures you may consider. Those measures are known as attribute selection measure. So once that measure you got among a few attributes, which attributes will be best splitting attribute, then data set is divided into that subsets, and that this procedure will be recursively applied to up to some stopping criteria. So stopping criteria means either you cannot classify the nodes, or you have achieved some depth of the tree. Okay, so you are limited by the depth, or you don't want the error rate is acceptable to some range. That time also you may stop. In the random forest, k data points from the training set will be selected at random. Then for each data set, sub data set, we can say subset, one decision tree will be constructed. Then for the unseen data, that for prediction, you have to use the voting mechanism. So for new data points, find the predictions of each decision tree and assign the new data points to that category that wins the majority votes. For example, here, if you see this are the food basket, all the instances are here. So it will be first k data set are picked, and for each k, various decision tree has been, n decision tree has been generated. So from tree 1, if this is the unseen data, tree 1 will give it as a class A. Tree 2 also it gives a class A, but tree n gives a class B. So out of this, majority voting is your then it apply the majority voting. So then it becomes the final class. Unsupervised learning. In unsupervised learning, here we don't know the class label. So so you will find the without the class label, we have to find the useful insights from the data. So it is almost similar to how we are thinking with our own experience. For example, this is the input raw data unlabeled. We don't know what is this. We do some interpretation and algorithm processing. Then we classify that as dogs and cats. Okay, we give the naming, the labeling name we are given, but it classify as part. Then the labeling name we have to give. So either it is partition-based clustering, hierarchical clustering, density-based clustering, distribution model clustering. In the partition, the data set into partition based on some principle, but in density-based, based on the density, it will be grouped together. So the density factor you have to define, and also some distribution based method is there. Depending upon the distribution, the data set will be grouped. This is the distribution model. Similarly, hierarchical clustering also there. Okay. So based on hierarchy, based on the properties, you have to hierarchical arrange the either top down or bottom up. That means either agglomerative or decisive algorithm we have to use. But performance evaluation, we have to either you have to make the confusion matrix. From the confusion matrix, you have to calculate the accuracy, that a true positive, true negative, false positive. That then what is the probability of correct classification? Then what is the sensitivity, means what is the ability of the test to detect a positive element from a positive population, and specificity is that the ability of the test to correct ruled out condition from a condition free population. So for model performance, our ROC curve also use that you can use the ROC curves for that one also. That it used for evaluating that machine learning model. That it based on the area under the ROC curve. If the area is high, the performance of the model is more, because it is a curve between the true positive and false positive. Okay, so false positive and true positive. So the larger area under this curve represents a better performance. That means the true positive dominates the false positive. But in case of sensor data, other evaluation parameters also taken into consideration. Because of computation capability, because that sensor data are generated and evaluated on embedded system. Obviously, communication rate, reliability between the embedded devices and IoT center are important metrics. Then, apart from this traditional machine learning techniques, that neural network techniques also can be applied to sensor data analytics. So processing multiple dimensions obviously requires a lot of computing power. It is also difficult to determine what parameters to input and what combined variations should raise a red flags. Okay, means how it combined the things. Similarly to supervised learning, supervised learning is efficient only with a large training set. Larger training sets usually lead to higher accuracy in the prediction in case of supervised. But training the machines was often deemed too expensive and complicated. So as we easily calculate how to distinguish between human and a car. So the humans have distinct shapes in comparison to vehicles. So for example, humans have legs, arms, those kind of things, and they have curved shape. But vehicles don't have those kind of things. But that time it is very supervised learning method. You can easily read the features. Based on the features, you can apply supervised learning method to distinguish between human and car. But once you distinguish between human and car, but now we'll give the distinction between human to human or another mammala. Okay, but that again, based on those features, it may not be possible because they are almost similar features. So the same goes for telling the difference between pickup truck and a van. If two vehicles are there, truck and a van, it is also difficult. In supervised learning, we'll go for neural network. So you can tell when you see one, but training a machine to differentiate them. So we can feel, but how to differentiate them requires more than basic shape recognition. So it is more than the shape also. Only with shape we cannot distinguish all the objects. So as we know, as all of you know, the neural network is the mimic of our brain. So when you look at a human figure, multiple zones of your brain are activated to recognize colors, movements, facial expression, and so on. So now our brain combined all the factors to that the shape you are seeing is a human and tells that what you are seeing in front of your eye is a human. So the information in the case of artificial neural network goes through different algorithms called units, each of which is in charge of processing an aspect of the information. So just like color, one unit, movement, another unit, facial expression, one unit, like that. For each activity, one unit should be there. They will process some information. The resulting value of one unit computation can be used directly or fed into another unit for further processing. For example, a neural network processing human image recognition may have 2 units in a first layer, 2 units opposite. So that depends the whether image has straight lines or sharp angles. If the image first passed the first layer successfully, a second layer may look for different features, just like a face, a presence of face, arms, and so on. And the third layer might be compared the images to images of various animals and conclude that the shape is a human. So how a neural network recognizes a dog in a photo? So in the training case, during the training phase, a neural network is fed thousands of labeled images of various animals. So it will learn the animals based on the labels, and it will learn to classify them. So one unlabeled image is there, and you have a pre-trained network. You have to pass that layer, pass that image. In the first layer, suppose say, the neurons respond to different simple shapes like edges or something. In the higher layer, might be 1 layer, 2 layer, 3 layer, depend how many layers in your network. Some more complex structure. As the layer increases, that each layer is responsible for more complex structure. But the final output will combine all the results and give you either it is a dog or a wolf or a cat or something. So once you add more layers, that tends to the cause of deep learning. Okay. So in sensor data, we also use deep learning techniques. So there are more layers in comparison than in a single layer. So the advantage of deep learning is that having more layers allows for richer intermediate processing and representation of the data. At each layer, the data can be formatted to a better utilized by the next layer. So obviously the process increases the efficiency. Next, we go for predictive analytics. So when data from multiple systems is combined and analyzed together, prediction can be made out of the state of the system. For example, in case of sensor deployed on locomotives, multiple smart objects measure the pull between carriage, the weightage on each wheel, and multiple other parameters to offer a form of cruise control optimization for the driver. Okay. So this type of prediction techniques, predictive analytics is used. At the same time also, cameras observe the state of the tracks ahead. Audio sensors analyze the sound of each wheel and the tracks. And multiple engine parameters are measured and analyzed. All this data can be returned to a data processing center in the cloud that can recreate a virtual twin of each locomotive, modeling the state of each locomotive and combining this knowledge with anticipated travel. So in the cloud, so I will come to the next slide. So when that one question is there, so so many data, so how to manage those kind of things. Now, already I answered those questions from the beginning. Again, I will repeat the same thing. So here, based on some factors, you have to predict what issue is likely to affect each train and each locomotive. So what is the useful? It will allows primitive maintenance and increase the safety and efficiency of operations. Similarly, sensors combined with big data can anticipate effects or issue in vehicles operating in mines, manufacturing machines, or any system that can be monitored along with other similar systems. So if you go for integration point of this machine learning, for sensors, sensor data analytics, so we have seen that various machine learning, obvious data analytic techniques is there, and in advanced that machine learning techniques also played a crucial role here. So where the algorithm are executed is a very important issue because each choice comes with each algorithm have various advantage which is because each algorithm has its own merits and demerits. So the easiest approach is that, so the sensor data analyzed to connect the cloud, it's connect to the all sensor device and to an IO that to a sensor data center, centralized obviously. And machine learning algorithms are conducted on that cloud-based system, computing resources. And virtually unlimited computing power makes the type of framework more efficient, okay, for the building the, but that cloud has, your assumption is that has high computation power. So if you see the centralized sensor data analysis, what should be the, centralized sensor data analysis, then, so here, this assumption is this is more, this infrastructure is more powerful. But another methodology you can use as distributed sensor data analysis. So here, in the distributed sensor data analysis, you push the sensor data analytics and that algorithms into the IoT node itself. Okay. So obviously, you may have very lightweight things you have to consider there because you are considering on the edges. Okay, so you can think edge computing time. So if the model is embedded in the sensor itself, then it will give you both raw sensor and decision models also. Then cloud will take the decisions. And in hybrid models are also possible. So here, both cloud data center and that sensor data both will use the data analytics model. And here it has both this IoT center, the machine learning models conducted. So this process requires high computation resources. So once the model is trained, on a set of sensor data, then that set of sensor data also transfer to the embedded system. See here, the model will be downloaded to the system, that sensor data, sensor nodes. So then after that, you may go for, based on this hybrid computation, you may go for edge computing. So where the analytics will be performed on the edge devices. So then another point is that since the data set is large, what you have to do? You have to, if your data set is large, then you have to go for big data analytics. Okay, then Hadoop, Spark, AR, those you have to utilize. So these are some references from which this talk. Most of the slides and materials are referred from these references. And now, if you have any questions, now I'll come to one question, and that what is the question? What should be the size of data for correct prediction? See, there is, you have to analyze the data. So you have to check what type of data is. It is a continuous data or numerical data or ordinal data or categorical data. If it is a categorical data, you can decide how much possible values for that attribute. Suppose say you have 20 attributes and the supervised learning methods you are applying, and you have one class level. Suppose say for 20 attributes, for each one you have, suppose 2-3 choices are there, 2-3 categories are there. Then the question is how many possible ways you can assign the categorical values to form a record, to form an instance. Okay? So the total number of possibility is calculated as VC dimension. That factor you may consider an approximation for correct prediction. Okay? But if you say give the fixed value you can take, but that based upon the VC dimension or all the possibilities that I told you, if suppose say you have only 2 attributes, one attribute takes 3 values, another attribute takes 2 values. So for how many possible ways you can construct the data set. Okay, so that means data is sufficient for the prediction because all the consideration values you have considered, all the possible values. So number of records you form based on your possible values, you can make it for your prediction. Then this is what should be the size of data for correct prediction. Okay. And since then the question is at the next forward question might be why you, if you are able to calculate the data set size, then why you are collecting more and more data. The reason is actually we don't know what are all the features of a particular application. If you know all the features of a particular application, then you can fix, okay, the 1000 data, 2000 data is sufficient to correctly design the model. What is the next question? Which machine learning algorithms to be used for wireless sensor networks to calculate energy efficiency? No. For energy efficiency, you have to first design your model. So just remember, I have already mentioned the slide, not a single one machine learning algorithm cannot suitable for one type of problem. It depends upon your data set. Same machine learning algorithm will maybe good for a best performer, a particular data set for the same domain, but same might not be if you change some features or something will happen. So you have to execute various machine learning algorithms and check as per your data, as per your energy, from which device you are getting energy. for what purpose. Okay, based on that, which one is giving the best performance, you choose that one. In machine learning model, we cannot tell that this is the best machine learning model. Otherwise, so many clustering algorithm, only one clustering algorithm will study which one is the best. It is not like that. I think I am clear to you. Any other questions? Already I have one question is there that if in the aircraft so many data is analyzed and a huge amount of data, so we are more ambiguous or not. The point is here nowadays due to the computational power and infrastructure and the technology, large amount of data in a fraction of second is not a concern. Because I told you cloud services there, edge computing devices is coming. Okay, so that is not a part, but the part is how you are using analysis and how you are interpreting the result and how you are using. So perspective data analytics, how you are doing.
So are there any more questions from the participants? You can unmute yourself and interact with the resource person if needed. So are there any more questions?
Sabine, if no doubt, you can wind up. Yeah, I think Dr. Shadu, thank you very much for your valuable session. Yes, Sabine. Okay. Yeah.
Yes. So thank you, Dr. Jayakrishna Sahu, for the wonderful session on sensor data analytics. We are extremely happy that you could render a session here and proactively taking up all the questions in the chat box. So on behalf of each and everyone, I would like to place on record our sincere gratitude towards Dr. Jayakrishna Sahu for his wonderful session. Thank you, sir. Thank you very much.
Yeah, thank you. Thank you.
So the feedback link and the attendance link for the session 4 is available in the chat box. All the participants are requested to mark your attendance by visiting the Google form. Make sure that you do it at the earliest because we will be closing down the attendance before starting the next session. So please don't miss the attendance forms. So our next session will begin at 12 p.m., which will be handled by Dr. Shajulin Benedict. So we are having a break right now from 11:30 to 12 p.m. and we will resume the session by 12 p.m. Thank you all. Thank you.